Hey everyone, how are we doing? We are starting officers. I feel like I'm so low down today. I'm just like, where am I? I don't know where I'm at. Let's see who's here. We're starting up MuBot. MuBot getting going in the chat. Office hours video. Top chat. Live chat. Pop out window. There we go. Sit up straight. There we go. Let's get working. I guess we need to do some of the homework or the quiz. Start off on the quiz at the very beginning. See some people join in here. Go over here to top chat. Just chilling out. Chilling out, Max, relaxing. All cool. Who's in the chat? MuBot's here now. So quiet. So quiet today. Getting the notes open. Doing some Mario Kart in here in a little bit. That's going to be exciting. Have some students coming in to Knoxville. Let's do some Mario Kart. Love it. People are already starting sampling distributions. Amazing work. No one's here yet, though. No one's in the chat. There, I can see the chat up here now. Who's here? Let's start with Chapter 12 quiz. Got it open. Do something more difficult than this. Let's start from the back. The harder questions. Okay, for a sales promotion. And here we almost go. Let's do it. Okay, this question says, for a sales promotion, manufacturer puts 31% winning bottle caps. It's like you get a soda, and underneath 31% of those caps say you're a winner, you want a free Coke. I loved that growing up. If you buy a 6-pack of soda, what's the probability you win something? Now, when you're working on these problems right here, you have to think about the steps to complete the problems. There's the YouTube channel. You have to think about the steps to complete them. So don't try to solve the whole thing at once. Do it in steps. Do it in little bits. So here we go. What you'd first write down for this problem is the two probabilities. So what we'd do is we'd make a sample space of everything that can occur. Sample space, once again, is defined as every possibility that could occur. It's not sample frame like everyone we could sample. It's the sample space, everything that could occur. So you have what we call the event, which is just something happening, and the probability of the event, which is the associated mathematical probability. We already see here that there is a 31% probability of winning, and thus losing is 1 minus that, which is called the complement. Good to see you, Andrew. What's Andrew Moore? Good to see you in the chat. Let's show you some points. Ask questions if we got them, but I think former student, right? I think. Someone's like, is that this semester or last semester? Yes, it is former student because your MuBucks have been reset. We gotta fix that here. We'll fix it out. But no, Andrew. Good. I know who Andrew is. Is it Red Bull Andrew? Is it Red Bull? I think it might be thinking of a different. That's Connor Moore. That's Connor Moore. I know so many Moores now. So with this right here, Andrew, feel free to ask anything. Good to see you, Andrew, because you're a former student, right? I think, maybe. With this in mind right here, if you're buying 6 sodas, 1, 2, 3, 4, 5, 6, what is the probability you win something? So we want to see you win something. Last semester, that's what I was thinking. I was like, I know, I remember. I was like, because I think about when I see the names. So you could win 2 things, you could win 1 thing, you could win 3 things, 4 things, 5 things, or 6 things. So you don't want to win nothing. So we either have the case, and this is where you start solving the problem, that either you win nothing, maybe Andrew remembers these problems, or you win something. And does this make sense, Andrew? What's the probability you win nothing or something? Like we say, well, you're either going to win something or nothing. Like you'll win something or win nothing. That probability would be equal to what? Like, what would this probability be equal to if we think about you're going to either win something or win nothing? Like, we had that up. And don't worry, we'll tell you some points anyways. I'll probably fix your points up. It'd be 1. Because one of those things must occur. Like, you're either going to win nothing or you'll win something. You got to have one of those things happen. So with this right here, we can then algebra it out a little bit. What we do to algebra it out is we'd simply go in here and change the or to addition because these are disjoint. Now, what I want you to do right now, if you're watching this problem and how to solve it, is to understand that on the review sheet or the formula sheet for the test, we give you these things in notes. So when you think about the addition rule right here, go to your review sheet, which we're going to put right over here. And on the review sheet, what you will see is down here, the rule for addition is that things are mutually exclusive, also known as disjoint. And we use the word or. So you're seeing that in practice right here. When I said or, I'm talking about addition, and these two things are mutually exclusive. As in, you can't win something and win nothing at the same time. They can't happen at the same time, which is what mutually exclusive means. So now, to figure out the probability of winning something, we simply go here and we algebra over to the other side by doing 1 minus this, or we're subtracting this from both sides, which is an algebra trick to just isolate the variable of interest, which is win something. So now that we have the variable we care about on the other side, we can figure out the probability of winning something by figuring out 1 minus the probability of winning nothing. To win nothing means we'd have to have all losers. So you have to think, what's the probability all 6 are losers? All 6 losers. So what's the probability all 6 of these are losers? Well, that's easy enough to do. The probability of 1 being a loser is 69%. The probability of all 6 being losers is 0.69 times 0.69 times 0.69. And the way this would look mathematically would be the first is a loser, and the second is a loser, and the third is a loser. And when we say and, we're multiplying. And each Coke that we buy, these are Cokes in my opinion, because everything's a Coke, right? When we buy these, each one of these we open is independent of the last one we opened, which is the rule of multiplication. The rule of multiplication states that to multiply two probabilities together, they must be independent to figure out the probability of A and B occurring at the same time. So we're actually figuring out the probability of A and B and C and D and E and F. Yeah, that's right. And maybe G. We're figuring out 6 things in a row occurring. The first is a loser, and the second is a loser, and the third is a loser, and the fourth is a loser, and the fifth is a loser, and the sixth is a loser. And to do that, we multiply all these together, which reduces to this right here, 0.69 to the 6th power. It's the same right there as the rock says.
It doesn't matter.
Same thing right there. So this is the answer to the question. We're just showing it more visually right here. If we were to write it out in long format by doing this, you don't want to do that. Just 0.69 to the 6th power. So let's do it. Be careful with your math. Easy to make math errors. 0.69, 2, 3, 4, 5, 6. That multiplies it. And then 1 minus. There is the answer to the question. Now we're going to do a bonus version of this question. Bonus. We're going to do basically the same question, but this time it's with light bulbs. So let's do the light bulb version right here. So, light bulb question. 842. Okay, so this one is the light bulb you purchased. Okay, so maybe just click into this video right here on this timestamp. The previous question we did, nearly identical to this. So with this question right here, the first thing you always do for any probability question is write down your probabilities. Write them down, know your probabilities.
Notation, brother.
Notation, brother. So let's go right here. Thank you, Leo, for notation, brother. That's where that comes from. Classic Stat Tool 1. So we got a 5-pack of light bulb. 13% of them don't work. We're going to draw out what is called the sample space, which is everything that could occur when you screw in that light bulb. Only 2 things are possible when you screw in the light bulb. You have the event of it working or failing. Failing means it doesn't work. So the light bulb fails to work. And then we have the probability of said event. So the P of E right there is the probability of this event occurring, which the probability of the light working we'll figure out in a second, because the probability of it failing is 13%, making the probability of work equals 1 minus the probability of fail, making them complements right here. The way you know you've written out a proper probability space is that the probability space adds up to 1. A proper probability space sums up to 1 because it's everything that could occur. Also, they don't overlap, meaning they are disjoint technically. They're complements. Complements are actually technically disjoint, meaning they can't occur at the same time. These are important terms to know. If you hear me say things like complement, you should know what it means. 1 minus something is the complement of it. Also, disjoint means if one thing occurs, the other thing can't. Like a light bulb can't work and not work. Those are disjoint. They're also complements because it's everything that could occur. And they're also a sample space because it's everything that could occur. A lot of overlapping ideas, but two things don't always make up a sample space. Like a team could do a win, loss, or tie, but you could also write the sample space as win or not win, which would encompass loss or tie, like either win or don't win the game. So understanding what these terms mean, there can be similarities, but a sample space is everything that could occur. A complement is one minus the probability of something, and disjoint means if one thing occurs, the other thing can't. And I guess I should say independent means if one thing occurs, it does not influence the other thing occurring. Important terms to know for this chapter. Okay, so now that we've got everything written out here, let's think about what we want to understand. What's the probability at least one light bulb is defective? So either at least one is defective or what? And this is where we're writing out another sample space of possibilities for 5 light bulbs. Either at least one light bulb is defective or what? Well, if you buy 5 light bulbs, I'm going to buy a weird looking 5 light bulb pack right here. There we go. It's a 5 light bulb pack. And either at least one is defective, which could be this. Here was 2 defective, which means at least one is defective. Well, what is something that would be either at least one is defective or what else? Well, either at least one is defective or they all work. You can't have at least one defective and all the light bulbs work, and you can't have all the light bulbs work and at least one be defective, meaning that these are disjoint and we can add them together. So either at least one is defective or all the light bulbs work. Remember, if things are disjoint, which is mutually exclusive, meaning they don't include each other, we can add them together easily using the addition rule, which is what I'm doing here. Now, also by describing it as at least one works, or excuse me, at least one's defective, or they all work, I've actually written out a sample space because that's everything that could occur, and the sample space sums up to 1. We also know that the word or is just another way to add things together. Now, we want to figure out the probability that at least one is defective, so we simply take and algebra this over, because technically, I never write this out like this, but we're subtracting from both sides right here, this. So we are technically mathematically doing this. So someone might be like, oh, I see it. I was really bad at showing my work as a kid. They'd be like, how'd you solve this? I said, I did in my head. They say, no, you didn't. I said, yes, I did. And they said, what? That's exactly how that conversation went in my head. They were like, you're going to principal. You never know. So there is the math right there and how we can get it. I like when it makes it there we go, last party. Okay, so now we have to figure out the probability they all work. So what is the probability they all work? The probability they all work is the first works, and the second works, and the third works, and the fourth works, and the fifth works. You plug in your light bulb, first works, and second works, and third works, and fourth works, and fifth works. So this is going to be, all work is going to be the first works, and the second works, and the third works, and the fourth works, and the fifth works, and there's the math for all works. All works then reduces mathematically to 0.87 to the 5th power, because we are, I'm forgetting my shorthands here. What am I doing? Oh, that's why. There we go. All works is 0.87 to the 5th power. And so everything but all of them working is at least one defective. Kind of makes sense. It's like, well, every other thing but all of them working. That's basically 50%. So the probability of at least one being defective is about 50%. Got a half a chance that at least one is defective. And there we go. Drop it in. It was 0.501, right? I think we got it. No, what was it? Oh, really? Really? Double check your decimals. If you emailed me, I'd give that to you. I'd be like, yeah, I saw it was 0.501. I just didn't look at the next decimal. This one's kind of neat. Kind of a neat one. It's a bowling one. I like bowling. Let's do bowling. It's a fun one. I do like this one a lot. It's pretty simple. Oh, I can copy this. And a certain bowler. Certain bowler has a probability of making a strike of 90%. Now remember the tools for this chapter and the ways to solve these. If you watch the other problems, you've already seen how I start solving these. As soon as I get probabilities, I start.
Notation, brother.
That notation, brother. You can see it here where I wrote out the sample space of everything that could occur. Sample frame are the people we have access to prior to chapter 10. So what we need to do is we need to figure out everything that could occur. What could occur right here is the events. And the events have said probability of the events. You're either going to get a strike or not a strike. And the probability of a strike, because apparently you're awesome. No, you're not, dude. Don't lie. Is going to be 10%, 90% for being a strike, 10% for me, but 10% for not being a strike. So 90% probability someone makes a strike, 10% probability they don't make a strike. And now we need to figure out some probabilities of going 3 frames without a strike. So you have to imagine what happens here. You're bowling, and you're an amazing bowler, and you don't get a strike, you don't get a strike, and you don't get a strike. Hear the and right there, and you don't get a strike, and you don't get a strike, and you don't get a strike. All we do is we take the probability of not getting a strike and multiply it by the probability of not getting a strike by the probability of not getting a strike to figure out the probability 3 times in a row. This does assume that each bowl you do is independent of any other bowl. Possible, but with bowling, usually you get like hot or cold, so I don't know. It's going to be 0.001 because I'll show you. Because it's 10th times 10th times 10th. There we go, 0.001. And there it is. That's how we do it. Multiplication rule. Next one says the probability of making her first strike in the 3rd frame is going to be give me nice numbers. Should be that right there, and let's show how we got that. So what we need to do is we need to draw this out visually. Her first strike in the 3rd frame. Well, it would be that we should do strike as an X. And the probability of the 3rd strike. So we would put do this. That means they didn't complete the frame. And so it would be they don't get a strike, and they don't get a strike, and they get a strike. Because the first strike in the 3rd frame is being visualized right here. So they don't get a strike, and they don't get a strike, and then they get a strike in the 3rd frame. So that would be 0.1 times 0.1, which is 1%. Ooh, I got it wrong. It's going to be 1% of 90, which is going to be 0.009? Pretty sure it's 0.09. So 0.009. Well, darn for my mental math. That's why we check it. I see what I did. I did like 2 strikes. The probability of having at least 1 strike in the first 3 frames. Now, this is another at least 1 problem here. We were just doing those a moment ago. At least 1 strike in the first three frames. So you have to write your sentences for these. This is the way to do the at least 1 problems and get them right consistently. At least 1 strike. So you either get at least 1 strike, or is anyone here to help me out? You either get at least 1 strike or what? You're either going to get at least 1 strike or what? Like, I got at least 1 strike. Yay! The other side's not the fun part. Or no strikes. You either get at least 1 strikes or no strikes. You're either going to get at least 1 strike in the first 3 frames or no strikes. And so we change the or to an addition because you can't get no strikes or at least 1 strike. That is an impossibility. And then we go here and we mental math it, or not mental math it, we algebra it. And remember, the first question we asked was the probability of no strikes. The probability of no strikes was not a strike, not a strike, not a strike, 3 times in a row, and there it is right there. So with this is actually going to turn into 0.0999, I believe. There we go. And let's go check the math. 0.0999. It's the complement of the first, because either you'll go no strikes or you'll get at least 1 strike. So they're complements. A and C are complements. Perfect game is going to be 12 strikes in a row. You get a strike, and 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 12 times in a row. It's actually easier if you Google it. If you just go over here and go 0.9 raised to the 12th power, you can just Google it. And there's the Googling of the answer right there. So you just Google, and Google's going to tell you the right answer. So because you get a strike and 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 you get a strike, assuming each one is independent. It says to the nearest thousandths, so we should be good, and that should do it. Got the 100. I really love this chapter. It's one of my favorites. It's just very mathy. So if you know how to do each problem and don't make math errors, which are common to make, we did that one yesterday, I think. The M&M one is nearly identical to that. The car ones, people get stuck on these car ones. Got some more time. We're do an event here in a little bit, a Mario Kart event. But let's do the car one. People get stuck on these. The car ones are interesting. Just rocking and rolling today. Sure. A consumer organization estimates. Okay. So we have cars getting repaired right here. Now, what do? The first thing you should do is write out what information you have. I can't state that enough. I know I sound like a broken record at times where I'm like,
notation, brother.
Notation, brother. But the more you get in the practice of writing these down, you know what you have. It's like laying out all your tools before you're about to work. And then you're like, I've got a circular saw. I got a bandsaw. I got a table saw. I got a jigsaw. Oh, I got a lot of saws. Do I have a drill? I got a drill. Okay, so let's see what tools we have today to work with this. The tools we got right here is that we are seeing how often these cars are repaired. So with this car right here and how often they are repaired, we're going to write out our sample space, which is going to have the event of how often the car is repaired with the probability of that car being repaired. A proper sample space adds up to 1 because it's everything that could occur, and probabilities are contained within 0, 1. That's rule 1 and 2 of probabilities. So the first thing we see right here is that these cars need to be repaired once, about 18%, where it says 18% of cars need to be repaired once a year. And then we have 8% for cars being repaired twice a year. And 3+ repairs is going to be 4%. Now, we don't have the 0 repairs, but since the proper sample space needs to add up to 1, we're just going to take these probabilities, 18% plus 8% plus 0.04, 4%, and we get 70%. We just subtract from this to get the remaining probability because remember, this has to add up to 1 total because it's a proper sample space. The first question asks us right here if we have 2 cars. I'll do some amazing drawings right there. There's car 1. Oh, look at that. There's car 1. Car 2 will be a sports car. It's not a sports car. Oh, look at that. There we go. Sports car. Yeah, it's a sports car. Got an SUV and a sports car right there. If you can't tell. So the probability, neither car will need repairs. Now, they've kind of changed the way this problem works because you could rewrite your sample space. They're being mean. They're always being mean over here. You could rewrite your sample space as in the event of repair or no repair and the probability of said event. So the probability of repair is going to be 30%. I almost misspoke. And it might make it easier if I rewrite this. You'll see why. Because no repair means it got 0 repairs. Everything below here, maybe we'll do that in a different color, but everything down here is in the repair space. Everything down there is in where it gets repaired. So this would be the probability of 30% because if it gets repaired once, it got repaired. And we're just kind of reducing this table down into something much easier to where I wanted a square. I thought that was a square. There we go. So now we've reduced the table down, much easier to read. We have the car gets repaired or it does not get repaired. So what's the probability neither will need repairs? Well, the first doesn't get a repair and the second doesn't get a repair. If you've been watching the other questions, we've been mentioning how the formula sheet here, which you can find under review 2, literally says that when you are multiplying 2 events, they must be independent, and you simply say and between them, and you multiply them to get the probability of both occurring at the same time. The first needed no repairs, and the second needed no repairs. So you just say it like a sentence. The first needed no repairs, and the second needed no repairs. The cars technically need to be independent of each other, that the first would not influence the second, which in the real world, if one of your car breaks, you'll probably drive the others more. So there are kind of hypothetical problems. 7 times 7 is 49. Move the decimal, 0.49. So classic. One of my favorite multiplication squares growing up. 7 times 7 is 49. I just wrote out like all my like math. My parents used to do that as like punishments. Surprised I don't hate math, but they'd be like, write out your times tables. I'm like, I guess I get good at it, just memorize it. Got in a lot of trouble. Learned a lot of math. Not really. The probability that both will need repairs. Okay, so the first needs repairs and the second needs repairs. We'll go show it, but got the answer. The first needs repairs and the second needs repairs. First need repair and the second need repair. There we go. So 3 times 3 is 9. Move the decimal, 0.09. And double check in your calculator, I'm pretty certain, but it should be 0.09. What's the probability that at least one car will need repairs? Now here's the thing. Either neither car needs repairs or at least one car needs repairs. And the answer here should be this. Let's check our work. At least one car needs repairs. Oh, wait. At least one needs repairs. I made a mistake. Good. Because either none of them need repairs or at least one needs repairs. That should be right. Got it. Oof, almost made math error. That's why you got to write it down, because let's write our sentences here that we've been doing for the other at least one problems, because I almost made an error. I looked at it and I was like, wait a minute. We have that either at least one needs repairs or neither need repairs. Either at least one needs repairs or neither need repairs. And that has to equal to 1 because one of those things must occur. And then we can add them. And with this right here, we're trying to figure out at least one needs repairs. So we can then algebra this over to the other side. Really? Okay, there we go. And the probability of neither needing repairs was 0.7 times 0.7, because the first didn't need a repair and the second didn't need a repair. And that's got it right there. So if we just throw in the numbers, we can see how this works out, that the probability at least one needs repairs is the complement of neither needing repairs. There it is. And that is going to equal to, there it is. There's the math. So good work. That's the harder version of these. The other one is easier. Did I not do I did do it. Good. I didn't save it. Okay, so this one is also literally the same question with the same kind of table, but they ask different types of questions. So we can do rot here. Someone clicked the other video and they're like, what? There we go. Let's do it. So once again, what do? We write down all the information presented to us. We write down all the information. So we're going to take all the information, write it down, and put it into a sample space. So with this right here, we write the sample space, which has the event and the probability of said event. And so the probability of getting one repair is going to be 15%, as is listed above. The probability of 2 repairs is 5%. The probability of 3 repairs or more is going to be 3%. And now we don't have the probability of 0 repairs, but that's the only one we're missing, because 1, 2, 3 plus, the only thing we're missing that's excluded from this. So we just take right here and add up these values. It's going to be, I shouldn't do math and talk at the same time. I see what it's going to be in my head, 0.77. I was seeing it, and then I just couldn't say it. I was like, 0.77. There it is. And then double check your work if you want to make sure these add up to 1. I have made errors, so you could double check, but looks pretty good to me, because 77 plus 3 is 80, 80, 95, 100 when you add them up. So now with these values on the screen, let's look at the questions. This is just a singular car for this problem. What is the probability a car does not need repairs? Well, we literally just found that by writing out our sample space. What is the probability that it needs no more than 1 repair? 0 or 1. What is the probability it needs some repairs? 1 through 3 plus. There we go. These are all the answers currently shown on the screen. Much simpler of a problem because you just add up the probabilities. So the answer should be 77%, 92%, and 23. 77, 92, 23. 77, 92, 23. Okay. I think that's right? I think it is. Yeah, we got it right. There we go. It's the easier version of it. It's just no repairs means it got 0 repairs. Needs no more than 1 repair, so 0 or 1. I do want to point out, hopefully you're still watching, You're like, next question. Just kidding. But notice how I'm adding these because they are disjoint. Once again, I keep pointing to the formula sheet, which is Mubot has posted in the chat. But when you are adding things together, they have to be disjoint. And I say like 0 or 1 repairs. It needs 1 or 2 or 3 plus repairs. The or is very important right there that we use and understand how we are doing this mathematics. So understand what you are doing to solve these. Let's look at another. Oh, this one's so easy. We'll do like quick questions. Let's do that. Let's do some easy ones. Let's just do some that don't like quick multiple choice questions. These are easy. So quick multiple choice questions. Okay. Study from a region suggests that 13% of the people in the region have green eyes. So if you select 2 random people, probability of having green eyes and green eyes for 2 people would suggest that only 1.69% of people who are selected at random would both have green eyes at the same time. Like it'd only be less than 2% of people selected at random. So it says you select a brother and sister, and the probability they both have green eyes. Is this a proper calculation? Once again, the multiplication rule assumes that people are selected at random, meaning they're independent. So is a brother's and sister's eye color independent? The answer is no. My brother has blue eyes. I have green eyes. Blue is the non-dominant eye color. It's the recessive eye color. So he has the blue eyes. I have green eyes. So, yeah. My wife has blue eyes. Might have recessive blue. I probably have recessive blue. Yeah, my parents both had to have recessive blue for them to have blue eyes. Genetics. But anyways, it would, I guess our children would have a 3 out of 4 chance of blue eyes. I don't know. I don't understand it. Genetics. I want them green eyes. I like green eyes. I got green eyes. So with that, brothers and sisters' eyes are not independent. And that's all we need to look for here is that, no, they're not independent. Literally all I saw in the answer was not independent. So the multiplication rule does not apply. So you cannot be doing the multiplication rule to figure out the probability of 2 things occurring at the same time unless you satisfy the rule of independence right here. And once again, it's on the formula sheet. So check that out and use that. Traffic checks at a certain highway stops. Just 90% of drivers are speeding. So the probability of 2 drivers speeding in a row, the first is speeding and the second is speeding. Notice how we multiply here and we can say the word and. So the first is speeding and the second is speeding is about 81%. So the probability of finding 2 random cars in a row would be 81%. Now it does say in a row, and I did say random, but are 2 cars in a row random? No. Because your speed on the highway is going to be dictated by the people's speeds around you. If everyone's going 20 miles per hour, I doubt you're going 80. If you are, that's kind of scary. Don't do that. But the speeds on the highway, the cars have an interplay, meaning they're dependent. It doesn't mean if people around you are speeding, you must speed. But it does mean if people around you are speeding, you're probably more likely to be speeding to keep up with traffic. And it means if there's a traffic jam, well, I highly doubt you're speeding at that point. If you are, then really bad. Don't speed. There are cases when the speed of one car is not independent of the other speed of another, so multiplication rule does not apply. Same concept. Another one to the addition rule. So let me ask this for the addition rule right here. What is required for the addition rule? It's that things are disjoint, which is the same thing as mutually exclusive. It's like when your parents say, we're going to get some ice cream. Do you want chocolate or vanilla or strawberry? They say, can I get Neapolitan? They say, no. So here's your chocolate, your vanilla. Wait, they can't even do vanilla. It doesn't appear on the screen. It's vanished. So here's the vanilla. Some vanilla right there. Chocolate, vanilla, strawberry. You can't get all 3. And I guess we should, for the not getting all 3, draw it like this, because there'd be no overlap. But if you could get all 3, there'd be an instance where people get like chocolate, vanilla, strawberry all together. I also like to talk about people getting animals, and you could get like a bunny, a cat, or a dog, and the probability of getting a bunny might be 40%. The probability of getting a cat, if you go to the store, might be 30%, and thus the probability of getting a dog is also 30% if this is everything that could occur as a sample space with the event and the probability of the event. And what we're saying here is you can't get a bunny and a cat. You can't get a cat and a dog. You can't get a dog and a bunny. So let's see, because we can then add these up to figure out the probability of a bunny and a cat, or a cat. Excuse me, I said and, but I should have said or. The bunny or a cat probability is 70%. The probability someone gets a bunny or a cat. What's the probability someone gets a cat or a dog? 60%. And let's see if this meets the disjoint rule that one can't occur at the same time as another. We have homes right here. Records show that 37% of the homes have multiple bathrooms, 9% have fireplaces. Can you have multiple bathrooms and can you have a fireplace? Yes. So this is the way you check disjoint to see if you can add them. Can you have multiple bathrooms in your home? Can you have a fireplace? They're not disjoint. So since they're not disjoint, this is not how we would do it. They are not disjoint. We cannot properly add them with this methodology by just simply adding them. Another example of disjoint would be things like win, lose, or tie. So to check to see if win, lose, or tie, if you play a game, you say, here's my team's record. We win 70% of games because we're awesome. We lose 29% of games, and we tie 1% of games. So there is our team's record. So are these disjoint? Can you tie the game and win the game? No. Can you lose the game and tie the game? No. Can you lose the game and win the game? No. Every single one of these is disjoint, meaning if you win, you can't lose. Like you lose by, if I do my thumbs like this, you could win and lose at the same time. No, no, no. When are things not disjoint? If we say something like people owning stuff, which is a great thing to do, like we say someone has a cell phone, a laptop, and a Switch, Nintendo Switch. Switch 2, they're in the future, and we misspelled Switch. They have a Switch 2. Could be awesome. And so the probability of owning a cell phone these days is like 80%. The probability of owning a laptop is like 70%. Cell phone's probably higher than that. And Switch 2, only like 20% of people own Switch 2 right now. It's future. And with this right here, these are all not disjoint. Can you own a Switch 2 and have a laptop? Yes. Can you own a Switch 2 and have a cell phone? Yes. Can you own a laptop and have a cell phone? Yes. So they're not disjoint because if one occurs, the other can also occur. When things are disjoint, if one occurs, the other can't occur. They're disjoint. That's what mutually exclusive / disjoint means. Things mutually excluding the other from occurring. What mutually exclusive means. Disjoint, I like to think of disjoint is this and jointed is this, where if you have A and B, it's like a Venn diagram where A and B occurs in here. This is not disjoint. And this is disjoint. And this means mutually exclusive, and this is not mutually exclusive. So mutually exclusive means the same thing as disjoint. It means that they have no overlap. They can't occur at the same time. Like it's impossible. Like go back in time. You cannot win a game and you cannot lose a game. Those are disjoint things. They exclude each other. If you win, you didn't lose that game. We're talking about a game, not multiple games in a row. Okay. Here we go. Got that answer right. Do a few more of these quick ones. Oh, same concept. Suppose that 36% of families own a tablet and 50% own a computer. The addition rule says that about 51% own a tablet and a computer. Can you own a tablet? Can you own a computer? They are not disjoint because they can occur at the same time. So can you be adding them together? The answer is no. At least not with this methodology. You need to subtract off, but not on the test. So if you're easily adding them together, they must be mutually exclusive. They do not meet this. So since they are not mutually exclusive, the addition rule would not apply right there. Oh, let's do nervous kicker. We'll go back to doing some longer questions. Do like a few more because then I got to head out. Nervous kicker. A nervous kicker. A nervous kicker usually makes 82% of their field goals attempts. If they make the first kick, their success rate goes to 90%. What is the probability? Oh my gosh, there's just random news popping up. What is the probability that he makes the first 2 kicks? Thank you, random news. I wish you could disable that news thing. So this one is a little tricky because they're saying to you, if they make the first, the probability of the second is going to change. So they're actually telling you what the new probability is. So the probability of make first, and then probability of make second. So what's the probability they make the first, and then they make the second? Notice that the probability has changed, so this is actually dependent, but they've given you the probability. They're saying, well, here's what the probability becomes. So the probability is dependent, but we have it. They told us it. They said when they make their first kick, we know historically they make 90% of their second kicks. So all we do is just do the math. Here we go. There we go. They make the first and they make the second with the associated probabilities for making the first and making the second. Well, that's a quick one. Same sort of question right here. This one's about missing the train. And let me do one or two more because I'm going to head over to the event. The event. That was so quick, though. It's almost like, whoa.
Wow.
A student figures. Okay, a student figures that they have a 66% chance of being let out of class late. If they are let out of class late, there's a 62% chance they miss the bus. What is the probability that he gets out of class late and misses the train? Well, if you saw the question right before this, they're giving us both probabilities. So if they are out of class late, that happens 66% of the time. And then if they're out of class late, they have a 62% chance of missing the train. And that's the probability if they're let out of class late. So what's the probability of them getting out of class late and then missing the train? Notice when I say the multiplier right there, I say and, because we are multiplying together. And it has given us the probability. So it is telling us, no. We're not going to do independence right here. I know it's the rule, and we are kind of doing it. But we know that they miss it 62% of the time. So rounding to 3 decimals, we change it. And they are giving the probability saying of the 66% of the time they get out of class late, they miss the bus 62% of the time. So we now know the probabilities. So it's not going to change if they get out of class late. We know what the probability is. Does that make sense? Like this probability is going to be this if they get out of class late. So let's do another. We've done a lot of these already. Are there multiple ones like this? I don't like those. Someone's like, we'll do them. We'll do one more and end right here. These are the landline ones. They're very similar. Let's see. These are easy ones. Law of large numbers. Law of large numbers. We did a lot. We did almost half the full quiz. Here we'll end with the landline one. We'll end with the landline because I know this one gets people a lot too. We'll end with the landline. Okay. A 2015 survey by the National Center for Health Statistics found that 71% of adults ages 25 to 29 had a cell phone. Now, I'm stopping there because if you say like a cell phone, no landline, it just makes it harder to do. But 71% of people have a cell phone. They are going to talk to how many people? 8 random people. What is the probability that all of these adults have a cell phone? I know it says in a landline, but it just makes it easier. So when you think about this, the first question right here we need to write down is we have the probability of the event, its associated probability of a cell phone or no cell phone. Cell phone occurs 71% of the time. No cell phone occurs 29% of the time. So what is the probability the first person has a cell phone? First person has a cell phone, and the second person, and the third, and the fourth, and the fifth, and the sixth, and the seventh, and the 8th person has a cell phone. The probability all 8 have a cell phone is the first having a cell phone times the second having a cell phone times all the way across, which is 0.71 to the 8th power. The first has a cell phone, and the second has a cell phone, and the third has a cell phone. And they need to be independent of each other, meaning that... Ooh, I think I got it. Yeah, we'll say I got it. 5 decimals. 1, 2, 3, 4, 5. There we go. Meaning that you wouldn't pick like a family because then that's not independent. You just pick random people and see if they had cell phones. What is the probability that none of these adults have a cell phone? No one has a cell phone. The first doesn't have one, and the second doesn't have one, and the third doesn't have one. Well, it's kind of the same idea of what we just did, but it would be the first doesn't have one and the second doesn't have one. So now we just do the reverse of it where they don't have cell phones. And we take the probability of not having a cell phone and do that 8 times to say they don't have it, to say the first doesn't have it and the second doesn't have it, and we do 0.29 to the 8th power. So the first doesn't have one, 2, 3, 4, 5, 6, 7, 8. Whoo, basically 0. No wonder it wants so many decimals. I think 2, 3, 4, 5, right there. What is the probability at least one person has a cell phone? How did I know that? It's because either no one has a cell phone or at least one person has a cell phone. So when you look at this right here, you can write your sentence that we've been writing. It's either the case that no one has a cell phone, which we just figured out right there, or at least one person has a cell phone. And we just do the math right here and algebra it out like this. And we want to get at least one person has a cell phone. That'll do it. With that, I'm going to head over. We're doing a Mario Kart event. It's going to be really fun. But thank you, everybody. Let me save this in here. We got a lot of questions. I did like 10 or 12 questions. So until then, bye for now, everyone. Bye.